Dr. Wallace here. We're going to do Chapter 6, and let's get started. Okay, so Chapter 6 is all about something called an isomorphism. A group isomorphism, it's basically the way that we think of equivalence of groups. So two groups are isomorphic means they're essentially equal in all ways that are important in group theory. So the definition of that is basically you can take the Kayles operation table for one and relabel it so that it is the Kayles operation table for the other one. And another way to say that is there's a one-to-one and onto function or mapping from the underlying set of one group to the underlying set of the other group, such that the operation is preserved. So here are the things that one has to prove when you are showing that two groups are isomorphic. First, you have to define a function, okay, and it has to be well defined. So if, for example, A and B are representatives of the same element in a group, this should be, then their values, once you send them by the function to the other group, will represent the same element. So, for instance, if A is 5 and B is 1, and these are all mod 4, okay, or so I should say. So these are numbers, right? But they are also elements in the integers modulo 4, let's say. Then phi of 5 should give you the same answer as phi of 1 when you put it in there. That makes sense? So these represent the same elements in here, right? Even though they are different numbers, okay? They could represent the same element in this group. Okay, so if there's some sort of notion of equivalence in here, then the same notion of equivalence should happen when you send it via the mapping to the other group, the target space. Operation preserving means A times B goes to 5A times 5B. Okay. Injective is another way, or injection is another way of saying one-to-one. And that is to say, if they have the same value in the target space, then they have the same value in the domain space. Okay, onto means that everything in G prime, if G prime is the map, right? So here you think of G going to G prime, okay? So if G prime, if there's something in G prime, then there's something in G that maps to it. Okay. So here, for example, is an isomorphism. So we take a group that's the cyclic group generated by the rotation by 60 degrees inside the this should be D3, shouldn't it? No, D6. This is right. So this is that's right. This is a cyclic group with order 6, since this is the symmetries of a hexagon. G prime would be the integers modulo 6. Would that give me an isomorphism? And let's prove it. So okay, so let's look at the well-definedness. Another way to say is it well-defined is it a function? In other words, does it pass the vertical line test in sort of college algebra speak? Okay, so what am I saying? Okay, so this is the definition. So we want to say, okay, well, we know that R60 to the J is equal to R60 to the K. If we go back to our work in cyclic groups and also in chapter 1, I think, where we defined these symmetries of irregular n-gon, we saw that this is true if and only if, so let's say in D6 even. And therefore, in the group generated by R60 subgroup, okay? That's if and only if R60 to the J minus K is the identity in D6. Okay, so that means that R60 to the J minus K is the same isometry of a symmetry of the hexagon that does the same thing as that one, right? But it's a little less obvious there. We can't really say that J minus K is equal to 0, right? Because that's true in D6 and R60. If and only if J minus K is divisible by the order of R60, right? Right, is a multiple of, yeah, so 6 divides J minus K. Since the order of R60 is 6, right? And that means that J minus K will be congruent to 0 mod 6. Hence, phi of R60 to the J, which is J, and phi of R60 to the K, which is K, okay, will be equal since J minus K is congruent to 0 mod 6. And that means I is congruent to J mod 6, right? Equal in in the integers modulo 6. Okay, so it's well defined. Is it one-to-one and onto? Well, when you're dealing with notice that this group generated by R60 has order 6, and this group has order 6. Okay, so it turns out that if we prove one of these two things, one-to-one or onto, then the other one comes for free since they have the same order. All right, if these were infinite order, you couldn't do that. You'd have to prove both. But since we have shown it's well defined, right, if we show it's one-to-one, well then, by the pigeonhole principle, everything in here will go to everything in there, and therefore everything in here has something in there that goes to it. But we could prove each of them separately. It's just, we sort of already did it, right? So we do, let's assume that phi of alpha in the subgroup generated by R60 is equal to phi of beta, okay? That means, well, since everything in R60 is of the form, okay, let me sketch this. Alpha, which equals R60 to some power, right, since that's the elements that live inside that subgroup generated by R60. Beta is R60 to K, and J is congruent to K mod 6, and, every step that we did up here, you can actually reverse. So that's if it only, 6 divides J minus K, okay, which means that's if and only if R60 to the J minus K is the same symmetry of hexagon as the identity in this group, and so once again, if and only if R60 to the J is equal to R60 to the K in this group, okay, and that's what we need to show. Alpha and beta are actually equal. Okay, so therefore, one-to-one. Okay, so one-to-one works. And it is actually redundant to show onto since the domain has the same order as the range and is one-to-one, well defined, our mapping must be onto. Okay, we could have proved it separately, right? And it would have been obvious, right? So another way. Let k be an integer modulo 6, right? Then certainly R60 to the k maps to it, right? So that means it's 1 to 1. No, that means it's onto. Okay. Now, operation preserving. Do not forget this one. Okay? This one's probably the most important in a lot of ways. Okay, so operation preserving this sometimes is saying that the mapping is a homomorphism. Okay, so if you have a mapping from a group to another one that preserves the operation, that means it is a homomorphism. It is only an isomorphism if it is bijective. But there is such a thing as just, is it? It's useful to know if it's operation preserving. Okay, so we're going to take phi of alpha, 5 alpha times beta, where alpha and beta are given. So let me make this incredibly clear. Okay, so here's what we have to do. We said let alpha and beta be arbitrary elements in our group. Okay, I can label them R60 to the J and R60 to the K because that's what all the elements in this group look like. So now we're going to find what 5 alpha times beta is. Well, that's phi of R60 to the J, R60 to the K, and the multiplication in this cyclic group is you just add the powers. Okay, which means the function itself takes just gives you the exponent. Okay, and so this is in Z mod 6. Okay, but notice 5 alpha 5 beta, if you do the operation in Z6, the operation is addition. Okay, so this is an additive group here, Z6. It's a multiplicative group, but the operation is preserved. Okay. So when I write up here, 5a times b is equal to 5a times 5b. Right, this dot here just means the operation in the group that is relevant here. This is the operation in G. Operation or multiplication in G. This is now the operation or multiplication, however you want to call it, in G prime. Okay. So this is saying, therefore, C6, which is what we called this thing, okay, from chapter 1, is isomorphic to group of integers mod 6, okay? So this would be, they are isomorphic groups. We may also write this symbol here to say they are isomorphic. Essentially, they're equal in all ways that are important with groups. All right, now this one here is another example of an isomorphism, but it is not, you know, to show that it is one-to-one and onto, you can't just show one and get the other one for free, because these two guys have infinite order. So one thing you have to notice is, so is it onto? We'll let, you know, y be in R, then x is half of y will map to it. Okay, one-to-one, definitely, right? If you have two numbers that are equal, right, then because you can do the you can factor out a 2, right? So one-to-one, let's say phi of x1 is equal to phi of x2, means that 2x1 is equal to 2x2. That's if and only if. I mean, just divide it by 2, I guess. It's 2 and equals x1. Well defined, definitely. Okay. Can't really think of representing two numbers here in R. I mean, I guess you could use fractions for rational numbers and decimals, but multiplying it by 2, it's not gonna. It's still a well-defined map. I mean, it is a function, right? So y equals 2x. So well-defined. Y equals 2x passes the vertical line test. So it works out. Operation preserving, certainly. Okay. So OP 5x plus y, and of course this is the real numbers under addition. Okay. So 5x plus y is 2 times quantity x plus y, distribute, and then you get that is the same. All right. How about this here? The integers to the integers multiplied by 5, so all multiples of 5. This would also give me an isomorphism. A very similar proof to this one will work there. And so this shows, okay, we can extend this to the general case that says every infinite cyclic group is isomorphic to the integers. Okay, so well, why don't I just say this. Let's go this way. Let's prove every infinite cyclic group is isomorphic to Z, and then this would be a special case, right? Here I'm specifically giving you the isomorphism. That's the isomorphism. But here, if we have an infinite cyclic group generated by A, okay, then we take a mapping that goes from the group generated by A to Z by doing A to the K maps to K. All right, and this will be an isomorphism. I don't know how to write today. This is an isomorphism. Okay. This is essentially what this is, right? Going backwards, I guess. So here, this is the, or we could do the mapping from Z into A by taking K and mapping it to A to the K. All right. So it, for example, we have Z going to subgroup generated by 5 in that group. We take a K and we map it to A to the K, which would be 5K. And once again, you cannot get confused by multiplicative. Well, it is confusing, but remember that there's a difference between multiplicative and additive notation, and it's just a rethinking about what we're doing, right? So if we're talking about the subgroup generated by the element 5 in Z, that's what this is, okay? That's because the operation in Z is addition, so multiplying by a factor is repeated addition, right? Okay. Any function from the real numbers to the multiplicative real numbers is never an isomorphism, and here's the proof of that. So suppose psi is an isomorphism. Okay, then that means it is one-to-one and onto and operation preserving. Okay. Onto means there is an element R in the real numbers so that psi of R is -1. Okay. But then by the fact that it's operation preserving, one half of r plus one half of r must also map to -1, right? But by definition of operation preserving, this also means that, because this is the operation there, it should also be equal if we multiply them in the multiplicative group, which implies that there is a number in the real numbers. Right? This is a number, right? It's a well-defined function, so psi of 1/2 of r must be a real number, okay? This, whatever this number is, squared is equal to -1, but we know that no such real number exists, okay? Okay. What about if we do the reciprocal of numbers in the multiplicative group? This is an isomorphism, okay? Certainly phi of xy will be 1 over xy, but that's the same as 1 over x times 1 over y. Okay, that works. We don't have any issues with sort of dividing by 0 here, because in the multiplicative group, remember, this thing is r without the number 0 under multiplication, right? So every number in the multiplicative real numbers will have a multiplicative inverse, right? And that's what we're getting here. That's essentially what this is, the reciprocal, okay? All right, not every bijection will be operation preserving, right? So here's an example here where, right, so f of x plus y is equal to the 5th root of x plus y, but that's not equal to the 5th root of x plus the 5th root of y for any non-zero choices of x and y. So unless one of x and y is 0, right? But this has to be true for everything, right? It has to be operation preserving, which means f is not operation preserving. Okay, it is a bijection of the real numbers, but not a group isomorphism. Okay, Kayles theorem basically states that every group is essentially a group of permutations. In particular, every finite group is isomorphic to a subgroup of Sn for some n. Okay. And here's how this works. Okay, here's the proof. It's in your book, but Let me paraphrase it for you. So let's take T sub g of x to denote the function induced on G by left multiplication by the group element G. In other words, Tg of x is defined by, you just take G and multiply it to x on the left. All right. We need to show that this is a permutation. Okay, so Tg of x is a permutation of the elements of G. Okay. Well, if it's a finite group, this is pretty clear because we've seen on the Kayles tables that every row and every column is like a Sudoku puzzle, right? That it's a permutation. So each row and each column is a permutation of the elements of the group. Now, if it's a non-finite group, that's a little harder to justify. So we have to be more formal with that. So let me say so say to show Tg of x is a permutation of the set G, we just need to show it's one-to-one and onto. Okay. Well, suppose G of x is equal to G of y in group G. Well, left cancellation shows that x equals y. Okay, so that's one-to-one. Showed as onto. Question mark. To show this onto, notice that if x is in G, then Tg of G inverse x is x. Okay, so it is onto. So T of G is a permutation of the elements of G. Okay, and so then now we have to show that this mapping that goes from G to G prime, so G prime here is the set of all T of G of x's, right, where G is in G. Okay, and note this is a subgroup because it is a group under well, okay. Is it a group? Well, it is because it is a subgroup of the following thing. This is a group of all permutations of the elements of G, to show that this is a subgroup, you would just need to use one of the two-step or one-step criterions. Note that since T sub G of X is a bijection, it has an inverse, and so you can show inverses. Of course, this group here, over here, may have more things than just this small set here. This set here is has order the same order as G, but the group of permutations on the elements of G might be much larger. Okay, but we could show that it is a subgroup. It's certainly closed because Kayles table is closed. And what is the operation on this set? It is just like the operation here, which is composition of functions. So notice, so we're going to take two of these symbols here, and we're going to define it to be this, which is the same as composition, right? This is multiplication, G1 times G2, but that's just the same as composition. Okay, so we have that this is a subgroup of this permutation group. Okay, and we show that this is a isomorphism where we take a little G and we map it to the translation by left multiplication. I'm going to leave, I think, that to you guys. Okay, I think I'm going to stop here for this half of our video lectures on chapter 6, and so you can take a little rest and digest what we've done so far. And I'll make another one for the second half.